What is an FPGA? In this lesson, we'll explore the basic concepts behind field programmable gate arrays. The board shown on screen is called a breadboard, or the breadplate. A breadboard is commonly used to prototype circuits temporarily. On either side, you'll find power rails for extending voltage lines, and in the center are blocks labeled a E and F, J on the other side, where components and jumper wires can be easily inserted. This setup allows us to build a circuit, test its behavior, and modify the wiring on the fly. We can think of each physical component plugged into the breadboard as a Verilog module, and the wires connecting them as wire declarations. Placing components on specific holes is conceptually similar to the placement stage in FPGA implementation, while connecting one component to another with wires resembles routing in FPGA design. In a way, designing with an FPGA is like connecting ICs and wires on a breadboard, but it's all described using HDL, hardware description language. Inside an FPGA, there's already a vast array of configurable logic blocks and routing resources. Programming the FPGA essentially configures these elements to implement a desired function. Beyond that, FPGAs also include I/O blocks, clock management tiles, embedded block RAM, DSP slices, and sometimes even gigabit transceivers for high-speed serial communication. In some devices, you'll also find an embedded ARM processor. These are known as SoC, System-on-Chip, FPGAs. So while the internal architecture may seem complex, at its core, an FPGA is made up of programmable logic and interconnects that you configure to create any digital system you need. What you see on the screen is a PCB, short for printed circuit board. More specifically, it's a PCB with components already mounted on it. PCBs like these are commonly found in electronic devices such as smartphones, TVs, and many other consumer products. To create a PCB, you first draw a schematic, then design the PCB layout. Once that's done, the design is sent to a manufacturer to produce the actual board. But what happens if you discover an error after manufacturing? Say, a misplaced trace or component. In that case, to make a proper fix, you need to go back, revise the schematic and the layout, and manufacture the board again. Technically, you could cut a trace and solder a jumper wire as a patch, but doing that on commercial products would seriously reduce reliability. I'm using this contrast between breadboards and PCBs because it mirrors the difference between FPGAs and ASICs. Just like a breadboard allows you to change wire connections on the spot, an FPGA lets you modify your design immediately. If there's a mistake on a breadboard, you can simply move a wire. With an FPGA, you only need to change the HDL code and rerun placement and routing. This flexibility is one of the FPGA's greatest strengths. So why do we still make ASICs or dedicated PCB products? Because their performance is far superior and they're suitable for high-volume production. By including only the necessary functions and optimizing each data path, ASICs are inherently faster and more efficient. Also, once production volumes hit a certain point, say 100,000 units, ASICs become much more cost-effective than FPGAs. Think about smartphones. They're designed to be compact, power-efficient, and manufactured in massive quantities. That's why chips for smartphones, PCs, and similar products are produced as ASICs rather than built with FPGAs. So why do we use FPGAs? Let's explore their key advantages. 1. Development time and cost. Unlike ASICs, which could take 6 months to several years to develop, FPGA designs can often be completed in just a few weeks or months. This enables much faster time to market. Additionally, ASICs require high upfront costs, often millions of dollars in NRE, non-recurring engineering, expenses. In contrast, FPGA-based solutions are far more cost-effective, especially in low to mid-volume production. Of course, if you're planning to manufacture at very large scales, ASICs may still be the better economic choice. 2. Massive parallel processing. FPGAs are built to handle a high degree of parallelism. You could design custom parallel logic tailored to your application, potentially delivering greater performance than general-purpose CPUs or even GPUs in certain tasks. 3. Interface flexibility. FPGAs can be configured to support a wide range of interfaces such as PCI Express, Ethernet, DDR, HDMI, MIPI, and LVDS. For example, while an ASIC may have a fixed 4-lane MIPI input, an FPGA can be reconfigured to support 8 or even 16 lanes depending on design needs. Similarly, Ethernet ports can be added and scaled flexibly. 2-port for port, 1 gigabit per second, 10 gigabits per second, even 100 gigabits per second. This kind of customization is hard to achieve with fixed-function hardware. 4. Reprogrammability. As the name suggests, field-programmable gate arrays can be reprogrammed. If an issue is discovered after deployment, or if design updates are needed due to evolving requirements, you can simply update the bitstream. No need to fabricate new hardware. ASICs, on the other hand, are fixed after tape-out. Any changes require a full redesign and remanufacturing, which can be extremely costly and time-consuming. As technology evolves and requirements shift, FPGA flexibility becomes even more important. Waiting months or years to bring a new ASIC to market, only to find the standards have changed, can make the product obsolete on arrival. FPGAs offer a far more adaptable path forward. FPGAs are commonly used in fields such as industrial automation, automotive systems, medical equipment, defense, aerospace, networking hardware, video processing, and ASIC prototyping. They are especially well suited for applications that require high performance, support for a variety of interfaces, and are produced in relatively low volumes. FPGAs are manufactured by various companies, but AMD, formerly Xilinx, and Intel currently account for more than 50% of the global market share. Other vendors include Lattice Semiconductor, Microchip, and Efinix, among others. AMD and Intel both offer a full range of FPGA products, from low-end to high-performance devices, while other companies tend to focus on low-power or compact form-factor FPGAs. One of the most important factors when choosing an FPGA is the IDE, or Integrated Development Environment. A robust IDE enables RTL design using HDL, synthesis, simulation, IP integration, placement, and routing, all within a unified development flow. Therefore, it's essential to select not only a high-performance, cost-effective FPGA device, but also a vendor that provides a comprehensive and well-supported development platform. In this regard, AMD and Intel have a clear advantage over smaller competitors. Another key consideration when selecting an FPGA is IP availability, whether the device supports the specific IP cores required for your design. On the screen, you can see two breadboards. The one on the left is the same breadboard we looked at earlier. The one on the right is larger and has multiple ICs and wires connected in a more complex arrangement. A larger breadboard, of course, allows you to build more circuits. Likewise, FPGAs also come in various sizes and configurations, offering different amounts of logic resources and supported features depending on the device. The bigger or more advanced the FPGA, the more logic you can implement. If you look at the product portfolio on the AMD FPGA website, the families are organized from top to bottom as UltraScale Plus, UltraScale, and the 7 series. These product lines are categorized based on their semiconductor manufacturing process. UltraScale Plus devices are built on a 16 nanometers FinFET process, UltraScale on 20 nanometers, and the 7 series on a 28 nanometers process. In general, the smaller the process node, the better the chip performance. With finer geometry, more logic cells can be packed into the same area, and power consumption can also be reduced. This gives newer generation FPGAs significant advantages in both speed and energy efficiency. Within each FPGA series, AMD further categorizes its products into families such as Spartan, Artix, Kintex, and Vertex. These device families are differentiated by cost, performance, and target applications. Spartan and Artix FPGAs are optimized for cost efficiency and low to mid-level performance, making them well-suited for applications that require low power and compact form factors. Kintex and Vertex, on the other hand, offer higher performance, and are designed for more compute-intensive and bandwidth-heavy applications. These devices typically come at a higher cost but provide greater logic capacity, faster transceivers, and richer feature sets. By choosing the right FPGA family, developers can balance cost, performance, and resource requirements based on their application needs. As you can see in the comparison table of FPGA device families, there are differences in internal logic cell capacity and various architecture components across models. Before selecting a final FPGA, designers can run simulations, perform placement and routing, and even generate a bit stream based on the chosen target device. This makes it possible to evaluate in advance which FPGA is most appropriate for a given design. One of the most important factors in device selection is resource fit. The FPGA must have sufficient logic, memory, and I/O to support your design. In addition, the device should be readily available on the market. That means choosing a part with good supply chain stability, reasonable cost, and minimal lead time. Ideally one that's already widely used by many companies in the industry. So far, we've taken a brief look at what FPGAs are and how they differ from ASICs. While ASICs require long development cycles and high costs, FPGAs offer the advantage of rapid prototyping and faster time to market. In the next session, we'll explore the actual FPGA design process step by step. Thank you for watching.